In question 2a, we have a capacitor which was charged to a potential difference of 6 volts and then discharged through a 100 kilo-ohm resistor, with the potential difference across the capacitor recorded at frequent intervals. We're given a graph showing the first 40 seconds of this discharge, and in part 1 we need to calculate the initial discharge current. Well, for this we have the initial potential difference of 6 volts, and we can just use that the current is equal to the potential difference over the resistance, which is 6 volts over 100 kilo ohms, a current of 6.0 times 10 to the minus 5 amps. In part 2 we need to use the graph to find the time constant of the circuit. Well, the time constant is the time taken to drop to 1 over E of the initial potential difference, and the initial potential difference was 6 volts. So if we have 6 volts over 2.718, the value of E, we get a value of 2.21 volts. Reading from the graph, this occurs after around 22 seconds, so this is our time constant. In part 3 we need to find the value of the capacitance. Well, for this we can use the time constant is equal to the resistance times the capacitance, so capacitance is time constant over resistance, 22 seconds over 100 kilo ohms, a capacitance of 2.2 times 10 to the minus 4 farads. We can write this as 220 microfarads. In part 4 we need to show that the capacitor loses 90% of its energy after about 25 seconds. Well, the energy on a capacitor is given by half CV squared, and so we can say that the energy in the second case divided by the energy in the first case will be half CV2 squared divided by half CV1 squared. This simplifies to V2 squared over V1 squared, and this is 1.9 volts after about 25 seconds, reading from the graph, and starting at 6 volts. This gives a figure of 0.10, and this shows that the energy after 25 seconds is 10%, 1/10, of the original energy, meaning that 90% has been lost. In B, we're told that to produce a time delay, an intruder alarm has a capacitor identical to the one used in the experiment, but this time charged from a 12 volt supply, then discharged through a 100 kilo ohm resistor similar to the one used in the experiment. In part 1, we need to state and explain the effect of the higher initial potential difference on the energy stored by this capacitor. Well, the initial energy stored at 12 volts will be 4 times greater than that stored at 6 volts. This is because the energy is directly proportional to the potential difference squared, so doubling the potential difference quadruples the energy. In part 2, we need to state and explain the effect of the higher initial potential difference on the time taken for the capacitor to lose 90% of its original energy. Well, the time taken to lose 90% of the energy will be just the same as before, because this time depends on the capacitance and the resistance, both of which are unchanged.